Hello, good morning. We are starting with the new topic, powder metallurgy, and today I wish we will start in slightly different mode that I'll show you some videos that are going to give you a brief information about powder metallurgy, its processes and applications in industry, and thereafter we will continue with our conventional PPT. So we'll start with one or two short videos that are going to give you brief introduction and the processing details of powder metallurgy process.
Powder metallurgy, or PM, are the arts of producing metal powders and the utilization of metal powders for the production of massive materials and shaped objects. We look at the history of powder metallurgy and we see in 3000 BC the Hittites were using sintered iron. 400, the India Delhi iron column was manufactured. In the 1400s, the Incas produced gold and platinum jewelry using powder metallurgy processes. In 1805, the English used sintered platinum. In the 1880s, in the US, we were using sintered iron. In 1910, Coolidge and Edison invented tungsten filament lamps. In the 1930s, carbides, porous bronze, and steel were being used. In the 1960s, structural PM was introduced to the automotive industry. In the 1980s, we engaged in microstructural engineering of powdered metal. In the 1990s, metal injection molding and insulated powder came into being. In 2000, metal additive manufacturing started its growth. So one of the questions we ask is why PM? We look at the economic value, cost, precision, productivity, the captive nature of the material, refractory, reactive materials, and we look at unique properties, alloys, compounds, microstructures, composites, and geometry. You can see that the intersection of the economic, captive, and unique geometry is the ideal application. Components that fall into this area are definitely great candidates for powder metallurgy. One of the ideal applications for powder metallurgy is a porous capacitor. They use billions per day in the electronics industry. So we ask the question, why PM? It's the unique shape capability and a host of properties that provide users with creative solutions. Powder metallurgy is a very material efficient process with low process waste, alloys, materials, geometry that are not feasible with other processes, close tolerance capability, highly repeatable processes from part to part and lot to lot. Powder metallurgy provides excellent bearing qualities, very good surface finish, exceptional wear and strength, true involute forms on gears and splines, controlled porosity, oil and resin impregnation, infiltration with copper, soft magnetic properties, and hard magnetic properties are all achieved with powder metallurgy. PM enjoys a competitive advantage over other manufacturing technologies when the following conditions prevail. 1. The shape capability of PM offers economic and/or specific engineering advantages. 2. When the properties are satisfactory or so unique, other technologies are not acceptable options. In this graph, we have technology comparisons. Across the bottom, we see part complexity from low to high, and we see yearly quantities on the Y scale. In the bottom left, we have HIP and SIP, and you can see that they're low part complexity and typically lower volume. And above that, we see in blue, the powder metallurgy, conventional powder metallurgy, and medium part complexity and very, very high volume. And in the top right corner, we see MIM, or metal injection molding, where we have very high volumes and very high part complexity. In the bottom right, we have metal additive manufacturing. And as you can see, we have high part complexity to low part complexity, but with lower annual volumes. And then these technologies overlay technologies such as investment casting and machining. The powder metallurgy industry is made up of firms doing business that range in size and structure from small privately owned firms to large public and private corporations. Powder metallurgy is used in a wide range of applications, from instrument gears to automotive connecting rods, firearms, jewelry, and machine tool parts, cutting tools. The automotive industry is a large market for conventional powder metallurgy. Approximately 75% of ferrous PM is consumed by the automotive markets. The current North American PM content per vehicle is approximately 40 to 45 pounds. The Asian and European vehicles use about half of what North America uses. However, the PM is increasing in the Asian and European markets. In powder metallurgy, common processes are conventional, press and sinter PM. They're typically used by the auto industry, outdoor power equipment, recreation products, agricultural and construction, hydraulics, electronic machines, and applications and appliances, both MIM and conventional powder metallurgy. The metal injection molding is typically used in medical devices and firearms. Hot isostatic pressing, or HIP, is used in production of tool steels, refractory metals, and metal injection, or MIM, components. Cold isostatic pressing is used to produce stainless steel and aluminum components. Metal additive manufacturing is used by the aerospace, defense, medical and dental industries, the medical devices market, motorsports, oil, and gas. We have powder production methods, starting with atomization. We have water, gas, centrifugal, and plasma atomization, mechanical, milling, machining, and grinding. We have chemical production, precipitation, reduction, reaction, or vapor, and electrolytic deposition. From there, we have the shaping and forming of those metal powders. Injection molding, die compaction, cold isostatic pressing, hot isostatic pressing, slip and tape casting, rolling, extrusion, and metal additive manufacturing. After shaping and forming, properties and finish feature development are developed. Sintering is the forming of strong metallurgical bonds in the shaped PM components. Heat treatment, secondary operations such as various machining, deburring, grinding, sealing, and plating operations, as well as others, are performed. The industry supply chain are made up of powder producers, part fabricators, PM-related machine tool manufacturers, engineering and consulting, tool making, marketing and sales, research, and end users of PM components. Powder metallurgy is a value-added engineering solution and a global commercial business. Engineers use PM parts in aerospace, industrial, defense, automotive, truck, medical applications, and in other areas of your day-to-day life.
The MIM OnePiece Nozzle has pushed this technology to greater heights. It is an impossible task to produce this product near net shape using other conventional methods. Possible methods would require the brazing of multiple machined components, which would end up with high material wastage and high cost. The MIM OnePiece Nozzle produced a good finish with a complex internal channel in a sustainable and economical way. This product has opened up an entirely new application for MIM process capabilities, and definitely the most complex part created by AMT PTE Limited to date. Development efforts focused on controlling the distortion of the plastic inserts during the MIM process, as high injection pressure and temperature greatly affects the insert integrity. On the contrary, it is necessary to maintain high packing pressure in the inner core channel, as any loss in pressure will encourage weakness, resulting in cracks. Finding the ideal injection parameters that resulted in an overall good part were highly challenging during the development phase. The other critical feature is the tip of the nozzle. The diameter of the hole and gap surrounding it are controlled in micron range, which are MIM'd without secondary operations. Looking at the cross-section, you will understand how the critical features were achieved with great definition. The OnePiece nozzle is applied in a selective catalytic reduction (SCR) system for commercial vehicles in Europe to comply with the Euro 5 and Euro 6 standards. Urea is connected to the central hole and compressed air is connected to the other channel. The compressed air is pumped into the nozzle, exiting through the ring at the nozzle tip. This generates a low-pressure region at the tip, producing a Venturi effect, which draws out the urea from the middle channel and sprays onto the SCR system, which will reduce the exhaust nitrogen oxide to nitrogen gas and water. The special feature is the undercut internal channel, which can only produce using our patented in-coring technology. No other metal forming process can produce this near-net shape with minimal secondary finishing operations, making
Good morning. So, welcome back. We are starting with the new topic, that is powder metallurgy. In powder metallurgy, as you can see on the left side, the name powder, so metallic powders are used, plus some additives for bonding are mixed together. They are compacted and either they are heated or not heated, and final stage, that is sintering, that is to give the particular shape to the object is carried out. So today we will have a brief introduction of the subject matter called as powder metallurgy. It is all about powder and its shape, size, microstructure, bonding ability, the properties of material that we have studied. Same properties we can study for powder metallurgy products also. So it is the oldest method of manufacturing the parts and components using a mixture of metallic powder and bonding agents with a pressurized compacting and or heating the compact mixture. Various shapes can be manufactured, and the history of this manufacturing process goes back to 300 century, that is 350 to 75, and it was in India that Samudragupta, King Samudragupta had made a coin with some pillar called as Garuda on the pillar. You can see the diagram or you can see the picture. This is the bird, this is the pillar, and the coin that shows some human figure also. So it is said that this was manufactured in 350 to 75, that is 300 century, by Indian Emperor Samudragupta for his people. The second very renowned and famous metallurgy, powder metallurgy product throughout the world is the iron pillar in Delhi. This is also a 200 years old iron pillar, or more than 200 years. It is said to be made and installed by Ashoka, Emperor Ashoka, and the very famous or peculiar characteristic of this pillar is it does not rust. It does not rust. એટલે આને કાટ લાગતો નથી. આ 200-250 વર્ષથી એમને ઊભો છે. In rain, in air, in temperature and all environmental conditions, still there is no change in its shape, size and color. This is the advantage or peculiar characteristic of powder metallurgy products that were manufactured or prepared in India around 200 to 300 years ago. Now coming to the recent years. In recent years what we have is the best application of powder metallurgy was done by Thomas Edison in the invention of bulb, that is lights. In 1903 in America, tungsten was used to manufacture the filament, and tungsten filaments are manufactured using powder metallurgy as the manufacturing process. So this particular process has a great history and a very good application in the current situation also. There are almost various or all the fields where powder metallurgy products are in demand and are used widely. We will try to see as many as possible and try to understand the things related to powder metallurgy in terms of product, application, manufacturing process, and different stages of manufacturing of the product in powder metallurgy or by powder metallurgy process. Okay, so I hope this introduction gives you a brief idea about what powder metallurgy is all about, right? So, whenever we are studying any subject or any topic, there is an objective and always a why comes. Why do we study this? Why do we do this? What we are going to get out of this? So that why should be answered in a positive manner. And in all the topics that we have been covering, we have started, we generally discuss that what are the objectives or outcomes of the topic that are expected, and we try to keep our teaching learning process in line with the objectives. So after completing this chapter, you will be able to understand the basics of powder metallurgy process, learn about various metal powder production methods, know the different steps involved in powder metallurgy part preparation, that is manufacturing of powder metallurgy product, understand the advantages and limitations of powder metallurgy, learn about the applications and products of powder metallurgy used in day-to-day life in industry and throughout, right? Just starting the other way round, what I have given you in previous slide is that you have a application and product, so this creates more interest rather than the process and other things. So what I would like to do is I'll start with this part first, so that at least you are able to visualize and get some pinching or motivation and ability to learn the subject in a better way. So automotive components is one of the major application where powder metallurgy products or powder metallurgy is used for manufacturing the products. Okay, so you can have such products which are used in automotive components like carburetor, fuel injection, and the gas outlet, hot gas outlets, and the engine, where other metals generally fail And another thing is, you see the complexity of the shape and size and dimensions and different features that are produced in this material or in this product. It is really very difficult to generate such shape features along with such small machined elements in a normally machined component, and if we are able to do it, it takes lot of time, cost and material wastage. So second is again one more application of automotive components, that is small parts which can be extracted out of this and can be used. You see, you have been using high strength, lightweight sports equipment. So, what are these? Like badminton rackets, like the baseball sticks. This is the baseball stick, you must have seen it somewhere. These are very lightweight but very high strength, and they are generally made from a material called as titanium. Then we have transmission gears, which are part of a complete transmission system or a transmission chain or the planetary gear mechanism. There we get we require a very high wear resistant material. If the weight is less, we are always at advantage. So powder metallurgy gives us an advantage of reduced weight with higher strength also. Then complex shapes that are used in aerospace equipment. You see the scale is shown over here. You see the size. It is around 5 inch only. And it has number of features. It has a specific geometry which is very difficult to machine and maintain throughout. So powder metallurgy helps us in doing or manufacturing such shapes and such objects in large number with a great advantage of very low weight, very high strength and large number of production, that is high rate of production. And medical implants and planetary gears. You see, these are the components of planetary gears, which are also very small components. If you wish to manufacture such parts by casting or by machining, it is going to take lot of time. There may be many defects and there will be lot of finishing operations that we have to perform to complete this object. Okay, so this is about application and components or products that are manufactured by powder metallurgy in today's industry life. Now we'll try to understand the basic flow of manufacturing. Okay, so what we have is, we'll try to understand the process flow. Although over here on each screen you have the process flow in the form of a broad description, that is powder plus additives, they are mixed together, compacted, heated, and the next step is sintering, or cold it is sintering. Okay, so what are these things? So first we have powders, metal powders that are used. So what are the different metal powders that we will see? Then we have to add some lubricants or additives which will make them close together and bind them. Thereafter mixing is done in a machine called as blending operation. You generally would have seen this in your home in the mixers and blenders, that we try to mix the things thoroughly and to a great extent where everything would be very much in same phase. Okay, once we have this blending action done to mix the powder and additive thoroughly so that everything is in one phase or everything is very well mixed together, then the next step is for compaction. Compaction means to apply a large amount of load and press the component in a required shape of die. This is done by filling the blended powder material in This is done by filling the blended powder material in a die or in a required shape. Say we call this as a die. Then it is filled in over here. So it will be filled in over here. The powder will be filled in and a large amount of force, approximately 25 to 30 tons or more, or it this depends again on the application where you are using these things. Okay, so this is what we intend or we do with this particular process of compacting, right? So simply I will try to draw it again with slightly better control. Say this is the type of product that we want to manufacture, and so this becomes our die, and it has a particular shape which can hold. So powder will be filled in over here, it will be compacted, thoroughly mixed powder is filled in over here, it is compacted, and then we have a plunger. That plunger is going to exert a force, and this force would be around, may start from 2 tons to 400 tons depending on the size, shape, and the compacting required for a particular product. So this is how we have the third stage, that is your compacting stage, and after compacting stage we follow with next stage, that is called as sintering process. Okay, so the compacting can be cold or it can be hot depending on the temperature at which this compacting process is carried out. So we have different options whether we should go for which type of compacting method. These things depends and is selected based on the product requirement, right? Thereafter, finally, sintering process is done, and the sintering process is a very important process wherein the final shape which has been achieved by the component by die compaction becomes or comes to solid state bonding, or it is bonded in the solid state. Second and last thing, after making some of the part from this, like it may be a rod, it may be a sheet, it may be the particular component shape, then secondary operations, whether you need to drill something, clean something, plating, machining, such operations are done so that your final finished product is ready for use. Okay. So I'll briefly explain quickly what are the different metal, or these are the powder producing processes. Atomization, reduction, electrolytic deposition, carbonyls, and mechanical alloying. We will study these four processes in more details, that is different types of processes used for making powders, metal powders. Like thereafter, some compaction processes that are used. Simply we know one process, and that is pressing, that what I have shown it over here. Then there is a isostatic process, that is pressing, isostatic pressing. It can be rolling, it can be extrusion, and it can be injection molding. So we will learn short brief introduction or brief information about all the processes which are used for compaction and slightly detail in case of pressing and isostatic pressing. Okay, and we will do the detailed study of sintering process and secondary machining processes. They are used, we'll just discuss as these things will be covered in your subject PT2 production technology 2 in next semester. Okay, so this is what we intend to do with this chapter. Okay, so quickly going through one more slide wherein I would like to give you a brief information about what are the different shapes and forms of the powder. Powder can be having some chemical composition, a circular, it can be irregular, rod shape, chemical decomposition and mechanical combination. So this bracket indicates what is the process that is used for making the powder. Flex, mechanical combination, dendrites, electrolytic process is used, then we get dendrites. Then in 3D system, when we try to understand this different forms of the powder, we get spherical, irregular, rounded, porous, and angular. So these are different shapes and forms in which powder is available. Okay. So as discussed in earlier slide, we will try to understand different, try to study, we will study different powder manufacturing processes and the various processes. The first important process is atomization. In this process, again, this is subdivided or subgrouped into water atomization, gas atomization, and centrifugal atomization. Thereafter, we have a reduction process wherein metals will be given a reduction cycle so that powders are formed and they are formed in a specific very high purity form. Electrolytic deposition, this is used for depositing very fine particles of the range of micro and nano size. Carbonyls is one of the another methodology wherein powder is processed. Mechanical alloying, that is mixing of two different alloys or same type of powder with different sizes, they are used in making powder by the process called as mechanical alloying. There are different miscellaneous, that is various other processes also. We will touch these processes to know the details of it. So particle shape and size distribution. Particles can be spherical, flakes and spikes broadly in a overall we get. Then the size of particles that are used, size of powder particles that are used in this process range from 35 micron to 400 micron. These are the generalized sizes. Special application may demand this to come down to 5 micron or so. Okay, then we have distribution, that is so distribution, here we try to get the information as to what are the what is the distribution of particle, considering that there are these three different shapes. Say a shape with spherical nature, a shape with spike nature, and spec with flake nature. So this is spherical, this is spike, this is flake. So how their distribution? If you see this region, you have a very good even distribution of spherical and spike type of particles, but it has a uneven distribution for flake type particles. Again, if you go in this area, you have a very good distribution of spike and flake, but spheres are missing. So this is called as distribution, and the distribution has a various different methodologies or different names, classifications based on the availability of number of particles in a particular area or throughout the job. This is the thing that we have done for today, and we will see the other processes during our next lecture.